Welcome back, everybody. Today we're going to talk about graphing techniques with transformations of parent functions, whether they are even or odd, and some of their symmetry. Let's start with transformations of our parent functions, stretching and shrinking. So this parent function is going to be y is equal to the absolute value of x. To type that in our graphing calculators, I'm addressing the TI 84, 84 plus, 84 color, any of those types. In Y1, we would hit the math button and then use your right arrow to highlight the NUM. Should be the second one from the left at the top. When you do that, the number 1 should say ABS, and that stands for absolute value. So you'd hit enter and then hit that XT theta N button to get X in. So you have the absolute value of X. I want to go ahead and take a look at our table from that. And our XY table would look like this. This is our parent. Now we want to go through and do that same thing, but this time we want to have 2 times x in there and take a look at our table. So for that g of x, our xy table would be 4, 2, 0, 2, 4. Go ahead and do the same thing for the table of h of x. Pause the video if you need to. And you would get 1, 1/2, 0, 1/2, 1. And we're going to leave this part C for now. So if you had to take a look and see what changed, if we're looking at x or y first, our x values didn't change. We didn't do anything with those. But from our parent function, from the parent to the g, what could you say that we did to get from 2 to 4, 1 to 2, keep the 0, 2, and 4, knowing we have this 2 sitting out front? Well, we multiplied the y value by 2. And that graph looks more like this. From our parent function, that looks, and I'm just making sketches here, more like that. So it looks like the graph stretched upwards from the parent for A. Then if I were going to look at the difference from the parent to the H function and the 1/2 that's there, well, I see these ones change to a half. And half of 2 is 1. So it looks like we multiplied the y values by 1/2. and it took this parent function and made it come out really, really wide. So it shrunk down towards the x-axis. So from that exploration, let's talk about filling in some of the stuff on our notes here. So we have a vertical stretch when we multiply by a when a is more than 1. Notice that the a is in front of the function. So this would be the y is equal to 2 times the absolute value of x. It stretches up in the y direction. A vertical shrink happens when we multiply by a, and a is a fraction between 0 and 1. That would be the y equals 1/2 times the absolute value of x that we looked at. Notice that the a is still out in front, just like in here, it's out in front right after the equal sign. And the graph shrinks down in the y direction or gets pushed towards x. Go ahead and fill in this horizontal stretching and shrinking parts. We'll talk about that at another time. But notice where the a is for these ones. Reflection. If I'm plugging this in again for our graphing calculator, our y1, our parent function, is the square root of x. So if I'm looking here, the square root of x looks like this. And when we plug in the negative in front of the square root of x, then it changes to down there. If I look at the second one, here's my parent function, again in the gold. And let's do blue. Here is plugging in the negative underneath the radical. So if we had to put into words what it is that's happening, I might say for A, the y values are changing signs because we went from positive y to the graph now being negative y. Versus over here for B, I probably would say the x values are changing signs because this parent graph is on the positive side of x and the new graph is on the negative side of x. Those are all negative x values. And so these would be the difference between the graph and the parent function. All right, a little bit more about reflections. When the negative is in front of the function, again, this would be this one. It's a reflection over the x-axis. So you took the x-axis and you flipped it over the side. So I'm going to go back here. Here is my x-axis, for example, A, and we picked up this graph and flipped it over the top of x-axis and made it down here. The y values are changing signs from positive to negative and vice versa. the graph of y equals f of negative x. Now the negative's inside there. And so that's our second example, like this. It reflects the parent function over the y-axis. So again, if I go back, here's my y-axis, and we basically picked up this parent function and flipped it over there. Symmetry. Graphs can have symmetry across the x-axis if you can fold the graph at the y-axis. Sorry, I said x, and I'm looking at y. They have symmetry across the y-axis if you can fold the graph at the y-axis and have it fit exactly onto itself. If you are looking at an equation rather than a graph, you plug in negative x for all of the x values and simplify. So you're simplifying here, and you would have to have the exact same equation you started with to have y-axis symmetry. So we have x-axis symmetry if you can fold the graph at the x-axis and have it fit directly onto itself. If you are looking at an equation, you would have to plug in negative y for all y values. And then when you simplify, the equation is, the exact same right here. The exact same. Sorry, I thought I had my highlighter. So let's try some of this. For y-axis symmetry, we are doing y is equal to negative x squared plus 4. So let's simplify this. The negative is inside with the x, so when I square it, that value would become positive. And because these two are exactly the same, then we do have y-axis symmetry. For x-axis symmetry, we make the y negative. I have no simplifying to do, and when I compare it there to the parent function, they are not the same. So no x-axis symmetry. For letter B, y-axis symmetry, we plug in the negative for x. I have no simplifying to do here, so when I compare the original to this one, they are not the same. So no y-axis symmetry. Now if I check x-axis symmetry, we have a negative in for y. When I simplify the negative y squared, because the negative is inside the parentheses, it becomes positive again. And again, when I check the original with this, they are exactly the same. So we say yes, x-axis symmetry. All right, x-axis symmetry here. That means we're plugging in a negative for the y. When I simplify, the negative is inside the parentheses, so that stays a positive y squared. And when I check the original with the new one, then yes, we have x-axis symmetry. Now for the y-axis, remember we plug in a negative x. And so the negative is inside, that's x squared plus y squared is equal to 16. And again, when I check these two, they are exactly the same. So yes, we also have y-axis symmetry. For this last one, if I start again with x-axis, then we're plugging in a negative for the y. That's 2x minus y is equal to 4. If I check those two, they are not the same, so there is no x-axis symmetry. And then if I plug in a negative for x to check the y-axis symmetry, 2 times negative x is negative 2x. So if I check the original with the new one, they are not exactly identical, so there is no y-axis symmetry either. Symmetry with respect to the origin. So if we have a function that has symmetry with respect to the origin, xy and negative y are both on the graph. What that means is you replace x with negative x and y with negative y and have the same equation result. So let's try it. You plug in negative for x and for y. Simplify this, a negative x times a negative x is a positive x squared. A negative y times a negative y is a positive y squared. And so when we check the original with the new one, then yes, this has origin symmetry. If we check this second example, we have negative y and negative x. Because the x is to an odd power, it'll stay negative. And then when we simplify this, because both sides are negative, we divide by negative 1. And I look again, and they're exactly the same. So yes, this has origin symmetry. Even and odd functions. So a function is even when you plug in x negative for all x and get the exact same equation after simplifying. The function is odd if when you plug in negative x, you get all opposite signs. It's neither if you get a mixture of the signs. All of this would be note card stuff that I would put on my note cards. All right, so let's try it. I'm going to plug in negative x for all the x's. Let's see, we have an even exponent, so this will work out to be positive. An even exponent with the x squared, so that'll work out to be positive, and so we still have these. And because these are exactly the same, then this is an even function. Now I'm going to come to this second equation and plug in a negative for all the x's again. See, we have negative x to the third power. That's odd, so that's going to make that a negative 6x to the third. Negative 9 times negative x is a positive 9x. So when we compare the original to the new, this 6 was positive, now it's negative. This was minus, now it's plus. All the signs changed. And so that makes this an odd function. Let's take a look at this last example. We have 3 times negative x squared plus 5 times negative x. So the negative x to an even power keeps it positive, so it's still positive 3x squared. 5 times negative x is negative 5x. If I compare the original to the new, the 3 is still positive, the 5 has changed. So this one is neither, because we had a mixture of keeping it the same and changing. The last part of our transformations that we're going to talk about are translations. So translations are moving right, left, or up, down. So we go up or down when we're adding something on the outside. So an example of that would be, this is filling in your blanks here. If we had y equals the absolute value of x plus 6, or y equals the absolute value of x minus 11. This plus 6 would be moving up 6. The minus 11 would be moving down 11. Right and left are going to be when we add something inside directly touching x. And notice that right has a minus and left has a plus. They're opposites of what we would think. So if I wrote some examples, again using absolute value, then this would be left 6 and right 11. So let's talk about the transformations that are occurring. One of the things we're going to ask you to do is be able to tell us this is the transformation that happened. This negative outside, not directly touching x, is an x-axis reflection. This is moving left 3 because remember it's opposite with the x's. And this is moving up 1. Go ahead and pull that 2 out of there. So it's just the absolute value of x minus 4. And this one is just going to go right 4. For C, we have an x-axis reflection. The 1/2 is a vertical shrink. And the plus 4 is an up 4. When we graph our transformations, we graph our transformations from left to right. So if I'm doing letter A as an example, remember our parent function which is so I have my parent function here. And so for the reflection, this would come next. Remember, the reflection takes all of my y values and makes them negative. Now we can't make a negative 0 because 0 isn't negative. But basically what that does then, this is my x-axis, and it takes these values and flips them down like this. So there's the red. And then we're moving left 3 after that. So I take all of these points and slide them left 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And 1, 2, 3. So there is my left 3. And last but not least, we have our up 1. And I'm going to put that in blue. So we take all of these and slide them up 1. And there's the blue. So that blue one would be our final answer. We're going to talk about the rest of these on the graphing calculator. And that is where I want to stop for today. Thank you very much. Have a fantastic evening.